Hello, so in this video I'm going to be explaining at what values this portion, which in programming we called R, that's a very small r, allow me to make that larger. Pretty much at what values for R does this equation is this equation stable, and at which are it unstable. So to demonstrate this, I'm going to actually erase this all. It's not crucial that that equation stays up there. So one thing to know is if we have the partial derivative of temperature in relation to time, and we have this equal to alpha, which is thermal diffusivity, we have the second partial derivative of temperature in relation to position. So what we can do is from this we can have T equal, in which T is temperature, large T is temperature, little t is time, X is position. Should have clarified those at the beginning. So we have the temperature being equal to the sum of -infinity to infinity. That's a k equals -infinity, and that I should have written this bigger. So we have the sum from k equals -infinity to infinity. We will have C subscript k, in which this is the thermal conductivity of the metal. And we will have that multiplied by e to the negative alpha k squared t, and we will have this times e to the I kx. And again, in which this is the thermal conductivity, we have e to negative alpha. Can't remember if I said alpha is thermal diffusivity. In case I didn't, now I did. K squared times t as in time times e to the I kx. So I will go ahead and erase this. All of this. So we have the equation t to the j n plus 1 is equal to t to the jn plus r, in which again r was the alpha times delta t over delta x squared, and we have that multiplied by t j plus 1 and minus 2 j, I forgot to write the t, minus 2 t jn plus t j minus 1 n, in which this temperature is a temperature at the current position, current time, temperature at the upcoming position, current time, temperature at the current position, current time, temperature at the previous position, current time. So now what we can do is, if we were to take out a t, take out the t of this equation, then we will get something else on the inside, which we could then form boundaries for and understand when it's stable, when it's not stable. So what we will end up having is, we will have t to jn plus 1. Well, no, not to the n plus 1. Here we are actually going to have tjn, which is current position, current time. And we're going to have that multiplied by e to the negative alpha k squared t. Actually, this is not normal t, this is delta t, which is change in time. So pretty much same thing, but delta t. We're going to have this equal to tjn plus r times tjn, which is the temperature at the current position, current time. I'm not sure if I'm going to have enough room for everything in here. So now on the inside, what we'll get is we'll get an variation of e to the something power for here. We'll just get -2 and plus e to something power. So we will have e to the ikx squared. Ik, well, not x squared, delta x. So essentially, this is what we will get if we take out t to jn from these values. You may notice this is little, they look very similar. I just realized I didn't put delta x here. It's bothering me. Delta x. So you may realize these values are pretty much the same, but they are still slightly different. Well, what we will end up doing is simplifying this more, so I have some room. We can simplify these values because e to the ikx equals cosine k delta x plus I sine k delta x. This is derived from the e to the ix equals cosine x plus I sine x. Same premises, we just also have k now, and this is delta x. So now, similarly, e to the ik delta x, negative ik delta x, I can't remember if I said that, equals cosine k delta x minus I sine k delta x. So now if we were to add both of these, if we were to add them up, we would get 2 cosine k delta x, and these values would cancel. Okay, yes, it's visible. So we add them up like they are in this. We would have 2 cosine k delta x. So I am now going to erase this. And now we can further simplify this area. So we will have t to the j n, and here we will have 1 plus r. And on the inside of that, we will have 2 cosine k delta x minus 2. There should be another parenthesis. So now from this, we can also distribute the 2 out from here. So if we do that, we would get 1 plus 2r cosine k delta x minus 1. And essentially for this portion right here, I wrote that very slanted, I apologize. So for this portion right here, this portion must be less than 1. So therefore, the cosine k delta x minus 1, not cosine, k delta x, the 2r cosine k delta x value needs to be less than 0. Because if we set this up and set it less than 1, we would subtract 1 and you would have 2r cosine k delta x less than 0. So therefore, the r value, as explained in one of the previous videos with the graph, it must be less than 1/2 in order to be stable. So to be stable, there's a lot of marks around this. So to answer the ultimate question, the value of r must be less than 1/2 in order to be stable. If r equals 0.6, it's an unstable value. So as long as r is less than 1/2, it is a stable value.